In this section, we're going to talk about sequences, and we're going to define what it means for a sequence to either converge or diverge. But before we get into convergence or if it diverges, we're going to talk about some of the basic terminology of sequences and some common sequences. That way, it's either a quick review or a brief introduction if you've never seen this before. So when we use notation for a sequence, it's going to look like this. Sequences are shown in braces, okay? And this n is called the index, and it shows you where you're starting and where you're finishing when you're plugging in values into your sequence. It could also be shown like this if you just assume that it's an infinite sequence. Now, n you can think of as the variable of the sequence, just like when we look at a function, we see x as the input. N is kind of like the input for a sequence, and it's called the index. Now, when we put in our n, the n is going to be the whole numbers. So you can think of a sequence as a discrete function with the domain of the whole numbers. So I can plug in 0, 1, 2, 3, 4, 5, but we're not plugging in, for example, 2.3 or pi or anything like that. N is always going to be a whole number. Now, when we plug in those whole numbers, we're going to get terms. And when we list out our terms, this is what it looks like. This A1 is the term that I get when I plug in n is 1. This is A2. And that's the notation we use for when we plug in n is 2, etc. Now, when we say an, that means the nth term in general, and sometimes we call the nth term our general formula. So what is the algebraic expression that we use to plug in our values of n? So let's talk about some very common sequences. We have the arithmetic sequence. When you look at an arithmetic sequence, you can see that it's arithmetic because the difference between each term is always constant, and we call that the common difference. The book might use something different, but I use the letter D to show the common difference. Now, you can think of this as a linear function, but it's discrete. So it's going to increase by the same amount with each value of n that you plug in. And the formula that you use for that looks like this. an, the nth term, here's our algebraic expression for the nth term. You take the first term, which is your a1, and you add it to the common difference times n minus 1. So here's an example of an arithmetic sequence. Notice that every time I go up to the next term, I keep going up by 4. That is our common difference. Every time I increase n by 1, I go up by 4. So my common difference is 4. My first term is 3. So when I plug this into my formula, this is going to be my 3. That's my first term. My common difference is going to be 4. And then I multiply that by the quantity of n minus 1. So I could either write my arithmetic sequence, my nth term for my arithmetic sequence like this, or if you want to simplify it, you get 4n minus 1 if you distribute that 4. So either one is fine, but this is the general formula that we use. Now we have something called a geometric sequence, and this is similar to the arithmetic sequence, but it has a common ratio rather than a common difference. So every time I go from one term to the next, you're going to see that it has a common factor. So I'm going to keep multiplying by a common ratio to get the next term. Just like in the arithmetic sequence, we add a common difference. This one is we're going to multiply by the same number over and over again. So we're going to call that common ratio R. And so our nth term, or our general formula for a geometric sequence, looks like this. This is my first term. I put that here in front. And then my common ratio goes in parentheses, and I raised that to the power of n minus 1. So here's our example. I notice to get from each term, I keep multiplying by a factor of -1/3. And this is actually called an alternating sequence because it goes from positive to negative to positive to negative. It alternates the sign. Our common ratio is -1/3. That's what I multiply to get each of the next terms in the sequence. So here is my first term. That goes in there. Here's my common ratio. And then I raise it to the power of n minus 1. So let's check it. Let's say I wanted to see if I get -2/27 for my fourth term. Here is term 1, 2, 3, 4. That means I'm going to plug in 4. Since I'm looking for my fourth term, I'm going to plug in 4 for n. So I get 4 minus 1 is 3. If I raise -1/3 to the third power, that's going to give me -1/27. And when I multiply it by 2, I get -2/27. So it works. If I plug in 1 to get my first term, I plug in 1 here. I get 1 minus 1 is 0. So when I raise -1/3 to the 0 power, I get 1, and 1 times 2 is 2. So it works. And you can do the same thing up here if you want to check your arithmetic sequence. If I want to check to see if I get 11 from my third term, I put in 3 for n. I could put it either here or here, it doesn't matter. And I get 4 times 3 is 12. 12 minus 1 is 11. Now, there are lots of different sequences, but these are the two most common. All right, looking at our first example, finding explicit formulas. Now, this is a key word here. Explicit means if I plug in a value for n, I'm going to directly find the value for that term, as opposed to a recursive sequence, which we're going to look at here pretty soon. All right, so for each of the following sequences, we're going to find an explicit formula for the nth term of the sequence. Now, I put down here in quotes, we're going to find the pattern, because that's basically what we're doing. We're looking for a pattern, and then we want to come up with some algebraic expression that represents that pattern. And so that would be our nth term. So in this first part A, I notice right away this is an alternating sequence. I've got a negative, positive, negative, positive, negative, etc. So whenever you have an alternating sequence like this, you're going to have somewhere in your expression -1 to either the nth or -1 to the n plus 1. It just depends on which one you want to start off with. What's your first term, negative or positive? So if I start off and n is 1, so n is 1 is my first term. Sometimes you'll see sequences that start at 0, so you'll have to pay attention to that. But if you're assuming that you're starting at 1, then I want to be able to plug in 1 and get out a negative number. So this works. Now, if my first term started off as positive, I would want to use n plus 1. So when I plugged in 1, I would get -1 squared, so it would be positive. So the evens would be a positive and the odds would be a negative. Odd meaning the odd terms are the even terms. Now, so this takes care of the alternating back and forth between positive and negative. Now, to find the rest of the pattern, I also noticed that on the top, I start with 1. It's just listing out the natural numbers, 1, 2, 3, 4, 5. So I'm going to make my numerator n. So as I plug in n is 1, I get 1 on top. When I plug in 2, I get 2 on top, etc. I also notice that the bottom is 1 more than the top. So I'm going to list my denominator as n plus 1. So now I have a potential formula or a potential nth term for my sequence. And it's always a really good habit to go in and spot check a few to make sure you've got it right. So maybe plug in n is 3 and n is 4 and make sure it works. But it's a good idea to make sure that you plug a few in and check to make sure it works. Because sometimes you think you've got it and then you realize you don't. Okay, looking at part B of this formula, the first thing that I notice is that the top are powers of 3, starting with 3. This is 3 to the first, 3 to the second, 3 to the third, 3 to the fourth, 3 to the fifth. So I'm going to make my numerator 3 to the nth. So when I plug in 1, I get 3 to start off with. When I plug in 2, I get 3 squared, which is 9. So there's my pattern for the numerator. In the denominator, let's see. In the denominator, I notice from 4 to 7, I jump up by 3. From 7 to 10, I jump up by 3. So it looks like in the denominator, I've got an arithmetic sequence. It keeps jumping up by 3. So if I use my formula that I know for arithmetic sequences, I start at 4, so that's my A1. And then my common difference is 3. That's what I keep increasing by. That's 3. And then I have to multiply by n minus 1. And I can rewrite it if I want by distributing the 3. And if I do that, I get 3n plus 1. So there really isn't any particular steps you need to follow for these. It's literally just looking for a pattern, using the information you know about geometric sequences, arithmetic sequences, just general patterns, and looking for alternating sequences. It's just a matter of gaining some experience of finding the pattern. All right, now in this next example, we're going to look at formulas for sequences that are not explicit. So remember, explicit means that I plug in the value of n and directly get the value of the term. Now, in these examples here, these are called recursive sequences. And recursive sequences are sequences that the terms are defined by at least one previous term. It could be more. So basically, instead of plugging in values of n, you're going to be using and plugging in values of the previous terms. So if we look at the example in part A, the first term is given to us. Now, depending on how many of the terms that it's dependent on, the author of the question has to give you the terms that it's dependent on to start off with. So in this case, it's only dependent on the first term. So you're given the first term, that's our A1 is 2. Now look at how the nth term is defined. It's not defined by n, it's defined by the previous term. A sub n minus 1 means it's not the nth term, it's the one before that. So when we're trying to define, let's say, the fourth term, A4, then we're going to use A3 here. 4 minus 1 is the third term. So we're going to take negative 3 times the previous term. So we're going to start with A1 is equal to 2. A2, this is telling me to take negative 3 and multiply it by the previous term. So I have negative 3 times 2 is negative 6. Then to get the next term, I take negative 3 times negative 6 to get positive 18. Then to get the fourth term, I take the third term times negative 3, which gives me negative 54. So as you can see, we're not plugging in values of n, meaning we're not plugging in n is 1, n is 2, n is 3. We're plugging in previous terms. So that's why this is not considered an explicit formula for the sequence. Now, to come up with the explicit formula for the sequence, we just have to do what we did in the previous term. Look at the terms and find the pattern. So I noticed when I was trying to find this, I noticed that all of these terms have a factor of 2. So when I was goofing around with it, I pulled out a factor of 2 and I found that the factor that was left over are all divisible by 3, or they have a common ratio. Keep multiplying by negative 3 to get the next term, which it basically tells us that in this definition here. So this, to me, looks like a geometric sequence where the first term is 2, and the common ratio is negative 3. Now, it's important that you use the negative because notice it keeps switching back from negative to positive. Without that negative, you're not going to get that. So I'm going to define this as a geometric sequence, and then we can check it to make sure it works. So I'm going to plug in r is my -3, my first term is 2, and I raise that -3 to the n minus 1 power. Now, if we check it, let's say we're looking for the term a3. That means if we want an explicit formula, I want to be able to plug in n is 3 directly if I want to find the third term. So when I plug in 3 here, I get 3 minus 1 is 2. -3 squared is 9, and 9 times 2 is 18. So that works. And then I definitely suggest you trying to spot check it more than once. But for the purposes of time, I'll let you guys do that. Now, looking at this next example, we have another recursive sequence. It's giving us the first term. A1 is a half. And then it's defining the nth term by taking the previous term and adding powers of 1/2. So for the second term, I'm going to add 1/2 to the second power. For the third term, I'm going to add 1/2 to the third power, etc. So for the first term, I have 1/2. For the second term, I take the previous term that goes here and add 1/2 to the second power, which gives me 3/4. For the third term, I add the previous term to 1/2 to the third power, and I get 7/8. For the fourth term, I take the previous term and add 1/2 to the fourth, which gives me 15/16. So now I have my terms written out, and I highlighted them in green so that it's easy to spot. But we want to find the pattern with these. Now, when I was working this out, I noticed that the denominator are powers of 2. This is 2 to the first, this is 2 to the second, this is 2 to the third, this is 2 to the fourth. So I wrote the denominator is 2 to the n. Then I noticed that the numerator is 1 less than the denominator. So then I wrote the numerator as 2 to the n minus 1. So here is our explicit formula for this recursive sequence here. And I'll let you guys do some spot checks to make sure it works. All right, now we're going to talk about limit of a sequence, which is then going to lead us into being able to talk about whether the sequence converges or not. So, and a basic question that we think about when we're talking about infinite sequences is the behavior of the sequence as n gets larger and larger. So it's pretty natural to think about the limit of the sequence as n approaches infinity. So if we want to graph it out by hand, we would just put n as our domain. So we would start at 1 and go up by 1 unit for n's, right? We're doing 1, 2, 3, 4. And sometimes we start at 0 for our n. But in this case, we're starting at 1. And we're looking at example A here. The sequence is 1 plus 3n. So when I plug in 1, I'm going to get out 4. So I'm going to plot the point 1, 4. Our y-axis is the term, the value of the term. So as you can see, 1 plus 3n, it looks linear. I'm increasing by 3 each time. Now let me show you how you can get this picture on your calculator. So the first thing you want to do is you want to hit the mode button, and you want to make sure you're in sequence mode. Typically we're in function mode, but in this case we want to be in sequence mode. So come down to where it says function, parametric, polar, and sequence, and make sure you're in sequence mode. So just make sure you're on sequence and then hit enter. Now when you hit your y equals, you'll see instead of having y1, y2, y3 where you enter your functions, it's going to be set up so that you can enter sequences. Now, for this one, this is asking you where you want to start. Sometimes we start at 0, sometimes we start at 1. In this example, we want to start at 1. Here's our explicit formula that we're plugging in. I can adjust the window to make sure that I see this picture. My n min in this case, if we want this picture, my n minimum is going to be 1. I'm starting at 1. And if we want this picture, my n max is 5. Now, this is how we want to set up our x-axis. So we're going to go from 0 to 8. So I want x min to be 0, my x max to be 8. Now looking at the y-axis, oh yeah, and I want that to be this SCL is our scale. Now on the y-axis, I want to go from 0 to 16. Okay, now I'm going to hit graph. And we should see that picture. Now when we hit trace, it will hop from term to term, and we can see those values. So this point right here that we're blinking on is 413. That's this one right here. And that's when n is 4. So you can use the trace button and your arrow buttons to hop back and forth and toggle between those terms. Now, if I imagine that this pattern continues, and I think about the limit as n approaches infinity, this pattern is going to go up forever. It's not leveling off anywhere. It's not approaching any specific value. So looking at it graphically, we would know as n approaches infinity, the sequence approaches infinity. So we would say the limit of the sequence is infinity. Now this one here, if I go ahead and graph it, for the second one, here's our terms. If I see these terms here, looking at it graphically, the output or the terms of the sequence are getting closer and closer and closer to 1 as x gets bigger and bigger. So we would say that the sequence approaches 1 as n approaches infinity. Now for part C, we have an alternating series. It keeps bouncing between -1 and 1. So it keeps bouncing back and forth like this. So as n approaches infinity, these values of the term are not approaching any specific value. So we would say that it approaches infinity. Then this last sequence, it's also an alternating sequence, but notice the size of the fraction gets smaller and smaller. So even though it bounces back and forth between negative and positive, the absolute value of those terms are getting smaller and smaller. So as it's bouncing back and forth, it's getting closer and closer to the x-axis. So we would say that sequence approaches 0 as n gets bigger and bigger. So you can get a good idea of what's going on with the limit as n approaches infinity by looking at the graph. Now, the official definition of a sequence given by the book says, given a sequence an, if the terms an become arbitrarily close to a finite number L is the limit, as n becomes sufficiently large, we say that an is a convergent sequence, meaning if it has a limit, it converges. L is the limit of the sequence in this case. If the sequence is not convergent, then we say it's divergent. Now, just like our limit laws when we were doing limits with functions, those same laws apply to sequences. So just a quick refresher of your limit laws here. I'll let you review those. Example where we're going to determine if the sequence converges and finding limits. Okay, so looking at the first sequence, part A, we have the sequence 5 minus 3 over n squared. So if I find the limit as n goes to infinity using our limit laws, I know that this converges. I know that this converges. So using our limit laws, I can break up the limit as a difference of two limits. And when I take the limit as n approaches infinity of a constant 5, I get 5. And when I take the limit as n approaches infinity of 3 over n squared, this approaches 0 because as these numbers down here get larger and larger and larger, the whole fraction gets smaller and smaller and smaller, closer to 0. So this gives me 5 minus 0, which gives me 5. So the limit of the sequence is 5, and we can say that the limit converges. This next sequence reminds me of a rational expression. So I'm going to use the trick where I divide everything by the term that has the highest exponent. So I'm going to divide everything by n to the fourth. When I divide 3n to the fourth by n to the fourth, I'm just left with 3. When I divide minus 7n squared by n to the fourth, I get 7 over n squared. And when I take 5 and divide it by n to the fourth, I get 5 over n to the fourth. When I take 6 and divide by n to the fourth, I get 6 over n to the fourth. And when I divide minus 4n to the fourth divided by n to the fourth, I get minus 4. So now when I take the limit as n approaches infinity, anything that has an n in the denominator will approach 0, because as the number in the denominator gets bigger and bigger, the whole fraction gets smaller and smaller. So what I'm left with is negative 3/4. In part C, I get 2 to the n over n squared. When I try to take the limit as n approaches infinity of this sequence, as I plug in numbers that are really large for n, I can see that this is going to approach infinity in the numerator and infinity in the denominator. And so I have this set up in a way that I can use L'Hopital. So I'm going to take the derivative of the top and the bottom separately. When I take the derivative of the top, I get 2 to the n times the natural log of 2. And then when I take the derivative of n squared, I get 2n. That should be an n, not an x. My bad. So this should be 2n. And then it looks like I still have the form of infinity over infinity. The top approaches infinity, the bottom approaches infinity. So I'm going to use L'Hopital again. When I use L'Hopital again, I get 2 to the n times the natural log of 2 times the natural log of 2. And then when I take the derivative of 2n, that gives me 2. And now when I plug in really large numbers, as n gets bigger and bigger, the numerator goes to infinity, and I have this 2 sitting down here by itself. So the whole fraction is going to approach infinity, which tells me that this sequence does not converge. There is no limit. Now, to figure out if the sequence in part D converges or not, we're going to have to actually use logarithmic differentiation. So I'm going to let y be this, 1 plus 4 over n raised to the n. And I'm going to take the log of both sides, and I'm going to get n times the natural log of 1 plus 4 over n, because using the laws of logarithms, I can bring the n down in front now. So rather than take the limit of this directly, I'm going to take the limit first of the natural log of y and then use that to find the limit that we're looking for. So when I take the limit of the natural log of y, that's the limit of the natural log of this expression right here. But because I want to be able to use L'Hopital, I rewrote it where the n is going to go downstairs in the denominator as 1 over n. So that way I have it where the numerator approaches 0, the denominator approaches 0, and I have it in the form to use L'Hopital. Now, when I take the derivative of the top and the bottom separately, I get 1 over 1 plus 4 times n to the negative 1. I rewrote that as n to the negative 1 to make it easier. And then I take the derivative of the inner function using the chain rule. So that's minus 4n to the negative 2. When I take the derivative of 1 over n, I get negative n to the negative 2. This negative n to the negative 2 and this negative n to the negative 2 disappears. And I'm left with this 4 in this fraction. So this 4 is in the numerator. So now I take the limit as n approaches infinity of this simplified version. And as n approaches infinity, this fraction is going to get closer and closer to 0, which means I'm left with 4 over 1. So I'm going to get that the limit of the natural log of y is equal to 4. Since the limit as n approaches infinity of the natural log of y is 4, then we know that the limit as n approaches infinity of y, which is how we define this, has got to be e to the 4th. So my limit of this sequence right here, doing some major manipulations here, we get that the limit is e to the 4th, and so we know that this limit converges. So in this next theorem, we're going to talk about continuous functions defined over convergent sequences. And so if we have a sequence an, and we know that it converges and we have a limit L, if we know that f is continuous at that limit L, then we know there exists an integer, capital N, such that f is defined at all values an, where n is greater than or equal to n. And the sequence f of an, if we plug that in and we find the values of that function and define it as a sequence, that will converge to f of L. So if I plug those terms into the function, then the limit is going to be what I get when I plug the limit into the function. So looking at an example here, we're going to determine whether the sequence cosine 3 over n squared converges, and if it converges, does it have a limit? So if we look at just this sequence in here, 3 over n squared, we know that this converges to 0 if we just look at the sequence 3 over n squared. As n approaches infinity, this approaches 0. Now, because we know cosine is continuous, then if I want to find the sequence of cosine of 3 over n squared, then this is going to converge to cosine of 0, which is 1. The next topic is we have the squeeze theorem for sequences. It's the same idea as the squeeze theorem for functions when we talked about limits with functions. It's the same idea. If we find that we have two sequences and we have a third sequence that sits between them for all of those values of n, then if the two sequences that it lies between converges to the same limit, then the sequence that lies between them has to approach the same limit. So we want to find if cosine of n over n squared converges. I'm going to say that it converges to 0, and I'm going to use the squeeze theorem to do it. If I blow this up, and I look at the sequence of 1 over n squared, that's in the green, and I look at the sequence in blue, which is a negative 1 over n squared, that's the sequence here. If I imagine the terms lying on these curves, then cosine of n over n squared is going to lie on the red, which is going to be between or equal to either the green or the blue. As you can see, it's going to fall between there. Now, since we know that 1 over n squared approaches 0, and we know that negative 1 over n squared approaches 0, and because this sequence falls between them, then this has to approach 0 as n approaches infinity. Okay, using that same logic, we're going to show that negative 1/2 raised to the power of n also converges to 0, because this is going to lie between minus 1 over 2 to the n and positive 1 over 2 to the n. And both of these limits, both this limit and this limit, both approach 0 as n approaches infinity. And because this lies between or is equal to these all over all the n's, then we know because of the squeeze theorem, and this is between 0 and 0, that this limit has to be equal to 0. So we are leading up to a major theorem called the monotone convergence theorem, and we've got a couple more things to talk about before we get there. But we need to talk about something that's called bounded, and a sequence is bounded above if there exists a number m, so that all the terms in the sequence lie below that value. That's why it's called bounded from above, because nothing goes above that value. A sequence is called bounded below if there exists a number m such that all the terms are greater than that value. And a sequence is just called bounded if it's bounded above and below. If a sequence is not bounded, then it's unbounded. We also have another theorem where convergent sequences are bounded. And that doesn't necessarily mean the converse is true. This just means if the sequence is convergent, that it must be bounded. However, the converse isn't true, where if the sequence is bounded, that doesn't mean it's convergent. So if you think about that alternating series between -1 and 1, that's bounded. It's bounded above by 1. It's bounded below by -1, but it doesn't converge. It doesn't, the limit doesn't exist for that sequence. So the converse isn't necessarily true for this. So now we're going to talk about what a monotone sequence is. So a monotone sequence is a sequence. So once you hit a certain term, and it could be all the terms, but once you hit a certain term, everything after that is either increasing or decreasing. It could also be equal to. So for example, if I had the sequence with the terms 1, 2, 3, 4, 5, 6, and I repeat that pattern, every time I go to the next term, it's increasing. I could also have 1, 1, 2, 2, 3, 3. Then every single subsequent term is either equal to the one before it or greater than the one before it. So if it's a monotone sequence, each subsequent term could be equal to or greater than. If it says it's strictly monotone, then it's only going to be greater than. It's never going to be equal to the previous term. So if you say that we have an increasing monotone sequence, that means the sequence of terms is getting bigger, or each term is equal to the next. So that's a monotone increasing sequence. And then the same idea holds true for monotone decreasing. So each subsequent term, as n gets bigger, the terms are going to either be equivalent or smaller to the one before. So that's monotone, and just if it says strictly monotone, then it's only going to be increasing or decreasing. The terms aren't going to be the same. So now that leads us up to what we were building up for, which is this theorem here, the monotone convergence theorem. And what this theorem says is, if we have a sequence and it's bounded, and if it's monotone, if both of those criteria are true, then we can say by this theorem, it's been proved that if both of those things happen, then the sequence is for sure going to converge. We can say that that is a true statement. So I want to walk you through two proofs using the monotone convergence theorem. First, we're going to prove that 4 to the n over n factorial, that this sequence here converges. And then we're going to take the time to figure out what that limit is. So if we're going to use the monotone convergence theorem to figure this out, we need to show two things. We need to show that it's monotoned, and we need to show that it's bounded. If we can show those two things, then we can say by the monotone convergence theorem, we can say that the sequence converges. Okay, so the first thing we're going to show is that it's monotoned. Now, when I graph this on the calculator, and you can write out the terms by hand too if you want, but when I graphed it, this is what the sequence looked like. So after the third term, to me, this looks like it's a decreasing sequence. So what I want to show is that when n is greater than 3, that each term after that is going to get smaller or is equal to the previous term. So I'm going to show that an plus 1 is less than or equal to an for all n greater than 3. So when I find the n plus 1 term, that means I'm going to plug in n plus 1 everywhere I see n, and I get this. Now, I can use my knowledge of algebra to break this down into two factors. I can break this down into 4 divided by n plus 1 times 4 to the n over n factorial, and we can check it. I have 4 times 4 to the n. And because these bases are the same, when I multiply, I add my exponents. So that gives me a 4 to the n plus 1. Now, when I take n plus 1 times n factorial, that's going to give me n plus 1 factorial. So I just took this statement here and broke it down into two factors. Now, when n is greater than 3, let's say 4, if I put a 4 in here, then I'm going to have 4 over 5. If I put a 5 in here, that's going to be 4 over 6. So anything greater than 3, 4 and up, if I plug that in here, this is going to be less than 1. And if I take some fraction less than 1 and multiply it by an, that is certainly going to be less than an. So I just proved that when n is greater than 3, that an plus 1 is less than or equal to an, which shows that it's decreasing, which means it's monotoned. So we proved the monotone part. Let's prove the bounded part now. To show that it's bounded, when I looked at this graph, it looked to me like the limit, just visually checking it, it looked like the limit was going to be 0. Like it's getting closer and closer and closer to the x-axis. Once I started thinking about it, I realized that 4 to the n is always going to be positive. A factorial is always going to be positive as well. So when I take a positive over positive, this whole thing is going to be greater than or equal to 0, which means it's going to be bounded below by 0. So we can say that this is bounded below for all the n's and the whole numbers. And therefore, since it's bounded below by 0, and we showed before above in step 1 that it was monotone, by the monotone convergence theorem, we can say that the sequence converges. Now, when we're finding the limit, all we care about is the n behavior. We don't care about the first few terms. If I omit those or not, it doesn't matter. We're worried about the n behavior. So I can say that the limit of an plus 1 as n goes to infinity is the same as the limit as n goes to infinity of an. They should both be the same limit. Now, if we think back to when we wrote an plus 1, remember we said that an plus 1 can be written as these two factors, 4 over n plus 1 times 4 to the n over n factorial. So when I write the limit as n goes to infinity of n plus 1, because I know this converges, right? The limit as n approaches infinity for this one is 0. We know this converges because we just proved it by the monotone convergence theorem. So I can use the limit laws and split this up into two pieces. So I can take the limit of this times the limit of an. I know that this has some limit L. And I know that the limit of this is 0. So when I take 0 times whatever this is, it doesn't even matter because 0 times this limit is going to be 0. And since we know that the limit as n approaches infinity of n plus 1 is the same as the limit as an, because all we care about is the n behavior, then we know that the limit as n approaches infinity of our original sequence is going to be 0. In this last example of the lesson, we're going to go through and show that another sequence converges using the monotone convergence theorem. So in this example, we have a recursive sequence where we're given the first term, and then we're given the n plus 1 term when n is greater than or equal to 2. So the first thing we're going to do is we're going to show that it's bounded. But remember, we need to show that it's bounded and monotone to use the monotone convergence theorem. But I'm going to start off with showing that this is bounded. So using this definition given to us, I'm going to show that this sequence is going to be greater than or equal to 1. So the first thing I do is I combine these two fractions together by finding a common denominator, and I get an squared plus 1 over 2an. Now, if I want to show that this is greater than or equal to 1, what I need to show is that the numerator is always bigger than the denominator. If I can show that an squared plus 1 is always greater than 2an, then this is always going to be bigger or equal to 1. So this is what I want to show. I want to show that it works for all the whole numbers. Okay, so what I'm going to do first, if I'm trying to show this, I'm going to subtract 2an from both sides, and I get an squared minus 2an plus 1 is greater than or equal to 0. And then this is the perfect square that I can factor. So I have an minus 1, and I can rewrite this as an minus 1 quantity squared. Now, because this is squared, this is always going to be positive or 0. So I can say that this is always greater than or equal to 0. This is a true statement, which means this is a true statement, which means this is always greater than or equal to 1. So therefore, since the sequence is always greater than or equal to 1 for all the whole numbers for n, then the sequence is bounded below by 1. So it's always going to be above 1, which means it's never going to go below 1. Now we need to show that it's monotone, and I'm going to show that this is decreasing monotone, meaning that an plus 1 is going to be less than or equal to an for all the whole numbers. Using the definition that was given to us, an plus 1 is defined as an over 2 plus 1 over 2an. Now, because we just showed that all the terms are greater than or equal to 1, if I take an and I cut it in half, and this is certainly going to be less than half an, when I add them together, it's still going to be less than an. So this an over 2 plus 1 over 2an is going to be less than or equal to an for all of the terms. So we just showed that the sequence is monotone, and we showed previously that it's bounded below by 1. So then by the monotone convergence theorem, we know that this sequence converges. Now let's find the limit. So just like before, we don't care about the first few terms. We're really concerned about the end behavior. And so whether I take the limit of an plus 1 or whether I take the limit of an, they should still be the same limit. It should still be L. So when I take the limit as n goes to infinity, using the definition, I take the limit as n goes to infinity of an over 2 plus 2 over an, we know that that should be equal to L. That's just the limit we're just a generic limit. Because we know it converges, it's going to be equal to some L. Now, because I know that each of these individually converge, then I can split up the limits and say, well, the limit of this is going to be L over 2. The limit of this is 1 over 2L, and that's got to be equal to L. When I solve this for L, I could get positive or negative 1. So a couple of major points to review what we talked about. Two things that are really important to remember. That if a sequence is bounded and monotone, then it converges, but not all convergent sequences are monotoned. And the second thing that's really important to remember, that if a sequence is unbounded, it diverges, but not all divergent sequences are unbounded.